Thanks, Levin. Right, so my talk today is called From Facepalm to Brainbender, Exploring Client-Side Cross-Site Scripting. This is actually joint work with a couple of people. So Stefan and Sebastian are actually even here, as well as my student Bernd and our colleague Martin. So while you did introduce me, I will do this again. So yes, my name is Ben Stock. I'm a postdoctoral researcher at the Center for IT Security, Privacy and Accountability, or for short CISPA, at Saarland University. And before that, I was a PhD student in the University of Erlangen-Nuremberg, focusing basically on web security. Actually, as you see by the collaborators, working a lot with Sebastian as well. Nowadays, I also do kind of more broad networks and system security. I think that's kind of the idea to be a postdoc. I'm actually a repeat offender here at OWASP. Had a couple of talks over the last years, and I hope to also get the chance to do it again next year. The base for this talk now is a academic paper that was presented at CCS last year. So if you have any if you want to get further information on what we were doing, you're very welcome to look for this. The title is actually exactly the same as the talk is here. All right, so quick agenda. I briefly want to start with an introduction and the history of client-side cross-site scripting, or what we call client-side cross-site scripting. Then I want to talk a little bit about the motivation and the contribution of this talk. Then I want to brag a little bit about previous work that we did to find cross-site scripting at scale. And then continue with some sciencey stuff. That is, we derive metrics on flow complexity and things like that. Then, if at that point you have fallen asleep, we will have a highlight section, which basically is the facepalms and the brain benders, plus a quick quiz to see whether you can spot vulnerabilities that I have here on the slides. And I will end the talk then with a quick outlook on how to do it right, and have a conclusion in the end. All right, so for the intro. So client-side cross-site scripting, or what we call client-side cross-site scripting, is actually known to the broader community as DOM-based cross-site scripting, and it's basically caused by insecure JavaScript code. And this is a snippet that is actually susceptible to such an attack. So what we see here is a call to document write. We start an image tag with a single quote here. Then have a hash value that is supposed to be sent to this third-party advertisement server, and we now append simply location hash /1. That is everything that is in the URL behind the fragment. And as Sebastian already explained, basically cross-site scripting is a means of code injection attack where attacker-controllable code that might originate, for example, from the URL is mishandled by an application and therefore can be exploited. So what does this regularly look like? So typically this would be the data flow that we see. So we have the black parts, which here are denoted as the things that are hard-coded in the document rather than originating from the user. And then we have the hash value here, and we have the closing remainder of the image element at the end. So in order to attack this, as the attacker, I kind of have the power to modify the hash value in whatever way I want to. So what I want to do in order to exploit this is first break out of the existing image tag. So I first close this with a single quote, the source attribute that I started here. Then I break out of the existing image tag. And now I can inject my own JavaScript code or HTML code. And in this case, obviously alert 1. And so now that I found this vulnerability, I can actually visit this website in my own browser or try to have my victim click on a link or force him to browse to this location, thereby exploiting this vulnerability in his browser. A brief history. So the term DOM-based cross-site scripting was first coined by Amit Klein in 2005. He called it DOM-based cross-site scripting or cross-site scripting of the third kind. This was because beforehand people only knew reflected and persisted cross-site scripting on the server side, and that's why he said it's like the third kind. Then in 2011, Stefano actually first released his tool Dominator, which uses taint tracking to find data flows. The idea was, as far as I understand it, that this would be a help to pen testers, that they would see, okay, there's a data flow, here's the operations that are occurring, so concat left, concat right, so they could find vulnerabilities. Based on this idea, actually, we extended on this together with Sebastian to do a large-scale study. So basically what we did is we patched Chrome, I will talk about this in a minute, to then automatically scan a large number of websites, in this case the Alexa top 5,000 domains, and we were able to automatically find vulnerabilities on more than 10% of them actually. Then in 2014, again with Sebastian, we kind of evaluated how well the XSS auditor performed in terms of stopping these vulnerabilities. Turns out that it actually was, we could bypass it for 75% of the vulnerable domains. Honestly, or to be honest, I mean, the XSS auditor is meant to filter reflected cross-site scripting, so it's not actually its job. But based on these findings, we then proposed a new mechanism of defending against this, which basically uses our taint tracking approach to filter out all code that might have originated from an attacker and thereby kind of stop the cross-site scripting. All right, so this as a brief history, and it also brings me to my motivation for this work. So the previous research in this area has focused on two things. That is detection and mitigation of the vulnerabilities, right? So we try to find it, and then we try to come up with a means of filtering against it. And there has never been any analysis of the underlying issues. So why do developers actually make these mistakes? Where do these vulnerabilities actually originate from? And rather than using kind of a toy example of code that we might have found somewhere, we wanted to find real-world vulnerabilities and analyze these. And kind of the topics of this talk that I want to go through with you is to answer a number of questions, and that is, the first one is, are analysts who try to understand the code and try to determine whether there is a vulnerability, are they maybe overwhelmed by the complexity of these data flows? Second question, are developers maybe not even aware of the pitfalls? You can probably guess yes, but I will come to this later. And thirdly, are there any special circumstances in the web's programming model that are different from other application domains, such as, I don't know, Android applications, that cause such flaws or help in causing such flaws? All right, so before we can discuss these questions, let me briefly introduce the data set, or more precisely, how we actually got to this data set. So first, the first component that we use is a taint-enhanced browsing engine. As I said, it's actually based on Chromium, and it marks all things that originate from a user, such as the URL, initially as tainted. And we do this on a per character level. That means if there is any string anywhere, either in the JavaScript engine or in the DOM, we can say specifically which of those characters in a string were originating from a user and which were originating from basically hard-coded source code. In addition, we saw information whether these were encoded somehow by the built-in encoding function of JavaScript. And we trace this data flows throughout the program. And if a sink is then being accessed, such as document write or eval, we basically report this. On top of that, we use a crawling extension to basically steer the browser to crawl a given set of websites and collect and transmit all this data flow information that we discovered to then store it in a central database. So this now leads us to a situation where this taint tracking engine reports a number of, well, what we call suspicious data flows. So they are from attacker controllable sources to a security critical sink, not encoded in any manner. So this sounds exploitable, right? And what we would see if this JavaScript code was executed and we visited a site where we set the hashtag to ABCD, we would see a data flow to document write, which is completely unescaped. Yeah? It's just ABCD. This is what we would see in our backend. However, there is actually for us, if we look at the flow, and this specific flow where we have ABCD, we don't know whether this was caused by a snippet that looks like this or a snippet that looks like this. So in this case, we actually see there is a regular expression test involved here, which makes sure that we can only use lowercase alphanumeric characters. So while in our database it looks like it's a dangerous flow, it is actually not, because we can't exploit it since we would need to have the greater and lesser than sign to actually inject our own HTML context. So basically, what does this mean? Not every flow is actually vulnerable, and we need to verify somehow that a data flow that we have in our database is actually a vulnerability. And to do that, we developed this infrastructure where we have initially a number of URLs that we seed basically into our database, for example, the Alexa top 5,000 domains. We then pass it on to the Chromium, taint-aware Chromium, to crawl these domains and report back all the data flows that it discovers. So these are now stored in our database. In the next step, these things are then handed to the so-called expert generator. This is something that Sebastian actually built. And basically what this does is, you remember the example in the very beginning. We saw that there was this hash value, and based on how this hash value was used, it was used in an image source attribute, and we needed to break out of this image source attribute by using single quotes, and then break out of the existing image tag. And this is exactly what the expert generator basically does. It takes a number of data flows, determines how the URL must be changed such that if there is actually vulnerability, it can be exploited. So the exploit generator then yields a number of so-called exploit candidates, which is basically a number of URLs which have the payload appended, as I had in the example in the beginning. And then we give these to the crawlers again, who, rather than now calling alert 1, actually call a function that reports back to our database that a certain exploit actually triggered, right? So we were able to execute our own JavaScript code, and therefore we have a verified vulnerability. And the result, that is also the basis for this talk now, was then a number of 1,146 vulnerable URLs in the Alexa top 10,000 domains on a slightly lower number of domains, so about, I think, 950 to 1,000 domains that were vulnerable. Turns out that actually on these URLs, in some cases, there was actually multiple vulnerabilities in one site. So there was the same payload that we used to break, for example, out of a image tag, could also be used to break out of an anchor, right, an A element. So we triggered different vulnerabilities in these websites. And yeah, so with these 1,273 real-world vulnerabilities, we had two issues. We wanted to do some metrics. So for example, how many lines of code were involved. So oftentimes, JavaScript is delivered to the user in a minified form, right? So there is no white spaces, there is obviously no variable names, which are very long and expressive, but rather everything is kind of reduced to the minimum size as to conserve bandwidth to the user. And this would have caused issues with the metrics. And another thing is that oftentimes vulnerabilities aren't really stable in the sense that they might be caused by third-party banners, for example, that are included in the website. And you sometimes have banner rotation where if you hit reload, you get a different banner, so it's not exploitable anymore. And therefore, in order to do kind of a sound analysis, we first needed to persist these vulnerabilities and normalize them somehow. And we did this basically in a 5-step process. So first of all, we cached and beautified the HTML and JavaScript that we saw with a proxy, but we only cached those versions which actually triggered a vulnerability, right? Because the other one, where we have the wrong banner rotation, doesn't make sense. Then we use a proxy with what we call fuzzy matching. So I don't know who of you has used jQuery ever to retrieve a resource. jQuery automatically attaches a nonce, basically, which is a timestamp, as kind of the underscore parameter, I think, to our GET requests. This is so that proxies will not cache the response, but rather there will be a new response. So what we did is basically we reduced all numbers in the URLs to the number 7, and therefore we could easily look up this in our database because it's always going to be 7. The next step then was to analyze the pages with the taint-aware engine to collect traces. And if you listen closely and look closely, you will actually see that there's a Firefox logo up here. So it turns out that while Chromium was fine to find these vulnerabilities in the first place, the optimizations in V8 made it really hard to collect traces. It was really tough to do that. So actually, Stefan then, as part of his master's thesis, I think, built basically the same intuition into Firefox, but that allowed us at the same time to really collect these execution traces where we could see line by line which code was being executed and was part of a given data flow. Next, we do a post-processing of the reports. So if you want to know, for example, how many operations were conducted between source and sink, if the sink is within jQuery, you will have like 6 function calls within jQuery, but this is obviously not kind of part of the problem, right? It's just the jQuery.html function, which is similar to what you would use for .inner.html. And therefore, we try to determine, okay, which part is jQuery, and just cut off this part, because otherwise we would kind of have weird results since jQuery adds this number of traces to the, or the number of operations to the trace. And then as a 5th part, we basically do the application of our metrics and do some additional analysis. So right now, we come to the kind of the sciencey part. Measuring the complexity of a data flow. So there are existing approaches to measure code complexity. For example, this is McCabe metric, which counts the number of linearly independent paths throughout a program. I have no idea what that is supposed to mean. But in our notion, what we wanted to answer is a question, how hard is it for somebody who can identify the source to follow this kind of the data flow throughout the program and then decide whether this is actually a vulnerability or not? And therefore, rather than using kind of these existing metrics, we came up with a number or we found a number of measurable properties which we could use to measure the complexity of a data flow. So the metric 1, this is very easy one, is the number of operations on tainted data. And the intuition here is the more operations you have, the easier it is to miss something. So For example, think of some operation where first the data is being escaped, then you have 200 operations, and then at some point in these 200 operations, the data might be unescaped again. So all of a sudden you have a vulnerability that if you only looked at, let's say, the first 5 or 10 operations, would not have been visible to you. Secondly, number of involved functions. So functionality in JavaScript can obviously be split up into smaller function units. But if you have to follow this flow of data, or of this code flow actually, through different functions, it makes it much harder to actually trace what is going on and to try to understand and jump back and forth in the code. Similarly, the number of involved contexts is an interesting observation. So we define a context basically as one inline script element or external script file. And the intuition here is if you have to jump back and forth between the script islands or script elements in the document as well as external scripts, you might also kind of lose your track if you're really doing a manual analysis and trying to follow this data flow. Fourth one, this is also pretty obvious, I would say, code locality between source and sink. If the source and sink operation are within 10 lines, you can probably see it on your screen, and it's hopefully easier to understand what might be going on. But this only makes sense, obviously, for those operations or of those data flows where both the sink and the source operation are within the same file. Right? If you have different contexts, then you can't measure the lines of code or the code locality between them. And then the fifth metric is what we call the call stack relation between source and sink. And let me briefly explain to you what I mean by this. So in this case, all sink operations that I will discuss are relative to this red box here, which is script element number 3. So if we consider that in script element number 3, you have the source and the sink, it's very easy, right? You have the source on the top, you have the sink on the bottom, easy to follow. It gets a little bit more complicated if you have the source in a function that then calls the sink, right? But still, you can, if you try to find first the source of the data, then you can follow from there, you can follow it down basically to this function call. So it's still easier than, for example, and this is now case number 3, the yellow case here, there is a function which basically does document.write and then get some random value from different function. So what you have to do is you have to first, you can't actually, in this case, you can't follow the data flow from the source anymore, because rather than, if you have identified a source, then you need to look, okay, which functions actually were, or which functions actually called this function that I'm now within, and then try to determine whether there is a vulnerability somewhere. And then there's a fourth case, where kind of source and sink functions have a common parent, but they don't, so none of them call each other. So this makes it even more hard. And then there's a fifth relation where we basically, I named this main function. So obviously in JavaScript there is no main function, but this is basically the main execution thread of JavaScript that is being run when you execute the web page. So in this case, there is actually no call stack relation whatsoever. So you can't even follow back a stack trace to see this data flow. And I will have an example of this in 2 slides. All right, so relation 1, as I said, very easy. You have a source here, you have a document write, very easy to spot. This one is a little bit harder. This is relation 5. So we have 2 distinctive script elements. In one, we actually define this variable global, which is assigned, for example, the location. And then somewhere else, we actually have a call to eval, which is in a sink in this case. And while this looks, well, easy enough, this might actually also include things where you have event handlers. So you might register, or you might have a global variable that is assigned somewhere in the program, and there's an event handler somewhere else which triggers on some event later on and then executes your, or kind of finishes the data flow. All right, so with these metrics, we actually plotted these. So this is the histogram. And what is, well, somewhat expected is that for the most cases, we have this tendency to have most of the data flows on the left. But I mean, yeah, you can stare at this and try to make sense out of this. I also tried it. Didn't work out so well. So what we rather wanted to do is we wanted to kind of put these results into perspective. And what we did therefore is we derived the 80th and 95th percentile. So that is 80% of the data flows had less than this value, or 95% of the data flows had less than this value for a specific metric, and used this as basically classification boundaries to then say, okay, it's low, medium, or high complexity. So it's basically, so this 80-20 is like Pareto principle going on. And the overall score in this case was, for any of the data flows, we kind of collected these 5 metrics, and we used the single highest rating of any classifier to determine whether the data flow would be complex or not, or how complex the data flow would be. And the idea here was to see, is it sufficient if for example, there's always one metric which tells us the data flow is complex, then probably if it overlaps with all the other things that were mapped to complex by all the other metrics, we don't need the other 4 metrics. We can just use the one metric. And these are basically the results, or the classification boundaries that we see. But then again, this is really just numbers. You can look these up also in the paper. I want to point your attention here a little bit further to the combined classification that we saw. So actually, let's have a look at the high complexity bucket here. So we see that at most 60 of the vulnerabilities are contained within the high complexity bucket for any one of the metrics, right? So just one single metric. However, if we apply what I told you earlier, that is the single highest rating by any of the classifiers, we actually see all of a sudden that we have about 200 of these which have a combined rating of high complexity. This basically means that these metrics, we need to have these different metrics to measure complexity, since, well, if we only had used one of them, obviously we would have missed quite a number of high complexity flows. But then the question was that I asked in the beginning, are analysts overwhelmed by the complexity? So now we have these numbers and we put them in perspective, but how can we actually answer this question? And the idea that we had to answer this question is, let's have a look at the comparison between vulnerable data flows and non-vulnerable data flows, right? As I said, and if you think back to the example that I showed you in the beginning, if you have these functions where you actually have a security check in front, so it can only be alphanumerical, are these secure data flows, which we also have, we have a lot of these data flows also in our database, are these more complex or less complex? And yeah, it turns out that if we look especially at the 95th percentile, we see for M1 and M2 that for randomly sampled flows, the values are kind of have double the amount. So 44 versus 22 is the cutoff point here. What does it mean? This actually means that in total, the randomly sampled flows have a higher complexity than the ones which were vulnerable, right? This basically answers the question. It's not the complexity, right? There is secure code out there which is much more complex. Obviously, if you have additional checks in place, this would also mean you have additional operations. Therefore, you have a higher number of operations. But this can't be the excuse that you say, yeah, it's too complex. There's nothing I can do about it. So basically, yeah, complexity might be a causing factor, but it's definitely not the causing factor in this case. All right, facepalms and brain benders. So for the facepalms, in our data set, and this kind of goes towards the question of are developers not aware of what they are doing, we found 350, so yeah, about 1/3 almost, no, 1/4, sorry, of these things. So we have these one-line vulnerabilities. There's document write, and then there's user input, vulnerable. Turns out we also had, and this is kind of a superset of the 350, we had 542 vulnerabilities which have less than 5 operations, and this mostly is kind of a concatenation operation of hard-coded, user input hard-coded. Remember the example from the beginning, you had exactly this, so it's very easy. And I have a personal favorite in this, and so there is w3schools.com, which is, as some of you might know, a website which is supposed to teach people how to use HTML and JavaScript, and they have this exact code on their website. This is, I think, where they explain how location href works. And this kind of makes my point very well, that it is actually developers unaware. It's people who teach the developers who teach them wrong. And it's similar to what Sebastian showed on Stack Overflow. It's like, yes, it's a solution, but definitely it's not a secure solution. But maybe W3 Schools doesn't really care about security so much as more, I don't know, functionality or something. All right, so for the brain benders, we actually had 59 cases where we had this relation 5. So yeah, this means we have no means to follow this data flow throughout the code. And sometimes these things are even event-driven, and I have an example of how this might look also in a minute. In the most extreme case, 31 functions were being traversed, and up to 291 operations were conducted on the tainted data. So I can understand somehow that you might lose track of what's going on. To be fair, these 209 operations were a horrible, horrible piece of JavaScript code, which was a long if-else cascade, which just checked for certain subdomains So whether it was, I don't know, was CNN or something, it's like, is it edition.cnn, is it sports.cnn? And there was really a number of these operations. All right, so the third question that I asked in the beginning is, are there things that are kind of rooted in the web's programming model that are different than other domains that might, well, at least help out with these vulnerabilities? And yes, there is. So there's involving third parties. So what happens if you include JavaScript code from a remote origin? So typically you have the same origin policy, which allows JavaScript code only to be executed within the origin of where it's executed or hosted. That's what I would say. But actually, once you use script source to include JavaScript from a remote domain, it runs in your origin. You trust this code fully. What does it mean for vulnerable JavaScript code? Well, somebody writes vulnerable JavaScript code, you include it in your website, you have a vulnerability and not the person who actually wrote the JavaScript code. And this is very much specific to this web domain, especially if you consider you include a URL once, and then do you have any control over changes that are done to this code? I mean, you can obviously use something like sub-resource integrity, where you specifically say this has to be the hash value of the file that I retrieve. But I think the advertisement provider might not like it, or I mean, basically, it will oftentimes break your code because they are still developing these things. And it turns out that actually, out of the vulnerabilities we had in our data set, over 1/5 were actually vulnerabilities that were purely caused by third-party code. For the most part, this was actually advertisement, not too surprising. And another thing that I found very interesting is that 25 of these flaws occurred due to an outdated, vulnerable version of jQuery. So there used to be a problem in jQuery with the dollar operator, where basically this is supposed to be used to select some element from the document, but actually you could even give it like HTML code. It would render that code, and thereby you had a vulnerability. Turns out that while only 25 of these flaws were actually caused by this vulnerable jQuery version, out of the 1,100 vulnerabilities or vulnerable URLs that we had, 472 actually used exactly this version. So there were a lot of vulnerable websites out there. Their luck was just that they didn't use this dollar operator. Right. And I said earlier that I want to come back to an example of a non-linear data flow. So this is kind of the first half of one vulnerability that we found. So basically what this does, even though it's really horrible if you look at it, so it first tries to split the location href, so the complete URL, at the hashtag. And the idea is then to here check if the part's length is bigger than 1. That means if there was a hash value set. I think there's other ways of doing this, but there's, that's just how they wanted to do it. Then next they set this variable keyword where they basically take the user-provided input, which is from the hashtag, and they decode it just for good measure. So if there was a browser that automatically encoded these things, such as Firefox, you would definitely remove kind of this. And then actually comes code that is secure and does not cause vulnerability. So what it does, it creates a meta element, basically a meta element which is supposed to hold keywords. And then it sets the content to keywords and appends this meta element to the head. Up to this point, this is perfectly secure. There's no way to actually abuse this. However, in comes the third-party script, which does actually this. So this function getKeywords actually looks at the meta element of keywords, extracts it, and then writes it to the document in basically plain text. I think the assumption of the third-party author was that the meta element with the meta keywords element was something that was controlled by the website administrator, right? The keywords for a website, why would they come from user input? But this also kind of highlights a problem where there might be kind of collisions in the views of how developers, first-party developers handle their application, and then how third-party code expects this to behave. Because if this was hosted on basically a regular domain where the administrator set the keywords, would be perfectly safe. I mean, it's ugly still, but it would be safe. And this alone is also safe, but the weird combination of these two actually makes for some, for this vulnerability to actually appear in the first place. All right, so now for the quiz time. I brought 3 examples of JavaScript, and I want to figure out if anybody can help me in finding the vulnerabilities here. So the first one is a function called escape HTML. It's a weird name. It actually should be remove scripts. But what it does is it creates a div element, then it assigns S, which is the user-provided input, to the inner HTML. Then it looks for all the elements, all the script elements in this HTML, which was now being parsed, removes all the script elements, and returns then the resulting HTML. Thereby, there is no cross-site scripting here. Is there? Mario's laughing, so Mario knows what's happening. Right, so there's actually something wrong here. Any thoughts? I heard inner HTML. Yes, that's very true. So inner HTML, as such, does not execute script elements. So if you really assign this inner HTML to script element to inner HTML, doesn't work. That's the way inner HTML is supposed to work. However, it does allow you to create event handlers. So what you do is you add an image element, set the source to foobar, set an on-error handler, and what the browser then does, it tries to resolve or tries to get the resource, foobar. Doesn't work. Oh, there's an error handler. I'll execute this. So here, there was actually somebody who, in trying to get rid of cross-site scripting, introduced a cross-site scripting vulnerability in a completely different place. So this is actually an interesting example. And also, I mean, even if this were somehow secure, right, he only removed script elements, so you could still do the image source trick. Is there something wrong here? So we have a variable slot ID. We're using parseInt to ensure that this is actually an integer. Then if the slot ID is set, then we pass on the user data to fill slot. Is it vulnerable? Well, it's obviously vulnerable because otherwise I wouldn't have it on my slides. Who of you have ever used Java? Okay, what happens in Java if you give parseInt in Java 1 and A, for example? I think from what I remember, it gives you a number format exception, right? Because 1A is not a valid number. Yet again, JavaScript has these nice features that actually, if you do this, parseInt 1 and then script something, this will actually return 1. It will only return basically it parses it as far as it can, and if at some point parsing doesn't work anymore, it just goes, okay, well, I'm done. I'm returning a 1 now. So actually, in this functionality, you would then have a document write as well. So again, it's a vulnerability. This one is my favorite one, and I think I even asked Claudio about finding the vulnerability here, and he couldn't right away. So is there a problem here? I'll briefly explain what is happening. So we're using jQuery to basically get this ID warning 404, and then the error URL, and we're trying to set HTML. And apparently, the developer was aware of the fact that there might be some cross-site scripting here going on. So what he did is he said, OK, I'm not just using location href, but rather I'm replacing the opening HTML brackets, or the lesser than sign, with the appropriate HTML encoding. Yeah. Yeah. All right, so the G flag is missing. That's very right. So the first parameter to replace is a regular expression, which, unless you have explicitly said that it's supposed to be global, will match the first occurrence. So all you needed to do was basically, in the URL, append a second, or yeah, but basically append one less than sign to your payload, and this would be escaped, and yeah, still exploitable. All right, cool. So let me briefly summarize basically what I was talking about, the underlying causes here. So our analysts overwhelmed by the complexity of data flows. We found that some flows are really quite complex, but it turns out that if you look at randomly sampled data flows, these are even more complex. So this can't really be the excuse. Are developers not aware of the pitfalls? Given that w3schools.com is not aware of the pitfalls, probably all the developers who learned to develop JavaScript and HTML from there are also not kind of aware. But we found evidence for improper API usage, such as the replace thing we saw right now, also the inner HTML, where people clearly were not aware of what was happening when they were assigning inner HTML. We found a number of these really stupid single-line flaws, so these proverbial facepalms. And we also found cases where people were explicitly decoding data. So I said this earlier, in Firefox, basically the whole URL is automatically escaped before it's being handled by JavaScript. And I think the developer wanted to have data that is in its raw format rather than the escaped one, but had clearly no idea why there was auto-escaping or why escaping of user-provided data might be a good idea to begin with. And we also found that there are actually special circumstances in the web's programming model because these third-party flaws that we see, they will actually cause vulnerabilities in the including application rather than the application or the site where they are hosted. Okay, now briefly best practices, or well, how not to do it, and then how there might be a better way to do this. So this is again a vulnerable example. Actually, this is also a real-world example. Don't ask me why this is done, but it's done sometimes. So we are document write. We just do the string concat here with location href. Obviously, this is vulnerable. The better way of doing this was actually to create an element, assign the href property, and then either append it to the body, or if you really want to go ahead and use document write, you can just use the outer HTML, which gives you the whole HTML. Then there is one bad example, or a good example of very bad programming. So this, so URL is the whole URL. I will go through the example. So what does the code do? It looks whether there is a kind of a question mark in the URL, and then tries to extract everything from the URL behind the question mark, which is also known as location.search, but apparently this person was not aware of this. Then what he does is he splits this at the ampersand. So the idea is to get the get parameters one by one. Then in this, while parsing or going over this query string, they split again on the equal sign. They check whether the length is now 2. That means there was a key and a value. And now comes the fun part. We want to set data.something. And basically, we're using eval. That's always an awesome idea. And if you heard the CSP talk, you probably know that there's a good reason why eval is kind of forbidden by default by CSP. So this actually allows the attacker to inject his kind of payload either in the get parameters key or the get parameters value. Because here we have kind of a string concatenation, and here again we have a string concatenation which allows an attacker to basically inject his payload. Actually, since we're looking at the search, different question. Are we only looking at the search bar, by the way, or the search part of the URL? Actually, we're not. We're just looking for the search and then everything that is behind it. So we are also actually taking in the URL fragment, which by default in Chrome is not encoded, so we don't even need to worry about encoding. The very easy fix to this is this one. Yeah, just kind of use this array-like indexing for the data object and assign the value, and this is secure. Good. Best practices for third parties. So first of all, if you have advertisement on your website, do ask your provider if they actually know what DOM-based or client-side cross-site scripting is. If they don't, think again whether you might want to switch your advertising provider. If they do know, then you have to ask yourself the question, does the ad really need to have full access to your main domain? So typically these ads are kind of included in your main page, and therefore your main page gets compromised. I know that some advertising providers, for example, want to know that their ad is being viewed, so they need to have full access to the document so they can see where the viewport is currently at. But for security, this is really, really bad. If you have the time, then you can obviously go through the JavaScript code that was provided to you by the third-party provider and only include it with SRI in place, thereby ensuring that it cannot change over time, it cannot introduce any vulnerabilities. Then update your libraries. So Alan posted this, I think, on Wednesday. I don't know who of you know Retire.js, but it's a cool way of finding out that certain libraries in a website that you're visiting are vulnerable, not necessarily your own. And this is, as far as I understand, the number of Fortune 500 websites, of the percentages that have at least one outdated library, which has a known vulnerability. So I would suggest to use Retire.js to kind of find out if you have any problems in your website. All right, so brief conclusion and summary. So we covered the basics and the history of client-side cross-site scripting and somehow motivated the work to look at the underlying causes, why these things actually happen, investigated a data set of 1,233 real-world vulnerabilities. And we found that there's actually several causes for client-side cross-site scripting. So there is somewhat complexity of the data flows that makes it harder to spot these, also in, for example, a pen test. But for the most part, it's really unawareness of developers who are really writing very stupid code. But also these third parties are a big issue where sometimes app providers, they don't care about security because, well, I mean, it's not their site that gets compromised, right? It's their customers. And finally, we covered some really bad examples of how not to do it, as well as some best practices. And with this, I'd like to thank you very much for your attention, and I'm happy to answer any questions that you might have. Not all at the same time. I can only answer one at a time. Yeah.
Earlier on, we had a slide that said that if you did want to blame complexity for the experience introduced with the justification, that was saying that you sampled a load of random code flows and compared them to the ones where you found vulnerability. So, in my mind, that doesn't exclude the possibility that there are some vulnerabilities out there that you just failed to find because the code flows were too complex for you to analyze.
Okay, so the question was whether, when I said that the data complexity or the data flow complexity can't be the causing factor because the benign flows that we found are more complex, there might still be flows out there which are too complex for us to find, right? That's basically it. So I absolutely agree that we are, with our methodology, not able to find all vulnerabilities because we don't have any guarantees about code coverage or specifics. Yeah? But the question is, I mean, we triggered these benign data flows in the same way that we triggered the vulnerable data flows, right? We just visited the website, and so my intuition would be that there might definitely be parts of the code which we didn't trigger, which might have vulnerabilities, but on the same note, we actually have a number of code or a body of code that is not being triggered, which is actually benign. So the problem is, I totally agree, there is no ground truth. You know? There is kind of a best effort to detect these things, but obviously there is room for improvement in finding these vulnerabilities, but still 10% of the Alexa top 10K, I think it's even 5% of the Alexa top 1,000 or something, 15%, sorry, that is already pretty good, but we have some ideas on how to improve on this also, to find some more. Mm-hmm.
How do you propose to cope with vulnerabilities in those services?
Okay, so the question was, or the statement was that there is not only third-party advertisement, but rather also there is third-party, for example, analytics or checking a website, and how you could handle these cases. That's actually a very good question. Basically, it's the same thing that what you would have to consider if you have your own website. The question is, do you trust the provider of the third-party script enough to know that they have a certain security process where they evaluate these things? And what's the added benefit for you that you have on the other end, right? And obviously advertisement, that's pretty obvious. You need to have advertisement to keep a website up and running because you need the revenue. But still in these cases, for the advertisement, you could always say, okay, I'll just put it to a different subdomain, put an iframe on it, and basically sandbox the whole thing, so it doesn't cause too much damage. For these things that actually really have a valid use case for having full access to your document, such as analytics, for example, it's really tough. So when you can go with manual code audit, I think we only found basically in our data set, there's really, for the most part, there's advertisement that were the causing factors for third-party scripts, for third-party vulnerabilities. There was some, minuscule amounts of other things as well, like chat integration or something into the website. But for the most part, it's actually advertisement, which is to be somewhat expected if you think the advertisement companies, obviously, I think if you have Google Analytics, there's a team at Google who kind of cares about security. And if you have randomadvertiser.com, they kind of focus on showing you advertisements and having functionality rather than security, probably.